Alright, another draft physics video production. Comments. Yuck. Just, yes, I need better viewers. So, anybody have any suggestion on how to seduce or acquire interest by somebody who actually knows something about physics and can actually make some arguments here, pay them for their time to some extent. I mean, it does take time to argue. As I'm pointing out, the videos do run on sometimes because you have to make arguments, and arguments take time. But anyway, any advice? Are you familiar with the Xeon experiments? So he thinks these are really important. So there's some people, backed by wacky money from the National Science Foundation and the EU and all these silly countries with silly bureaucrats running things who don't know shit about what means anything. They don't know anything about the science, so they get tricked by a Ken Wheeler. He shows up and I got the secrets, and they invest in this nonsense. So they're looking for dark matter, and so they're trying to create some sort of experiment, dark energy, that'll detect these things that you can't detect, like neutrinos. Just a complete waste of time. But anyway, and so he says like the Xeon experiments, like everybody should know what these are, right? These specific experiments designed to detect the magical unicorn dust, right? No, I'm not familiar with them, shithead. They claim to have found out how to calculate the half-life of an isotope, Xeon 124. They didn't figure out how to calculate it, you idiot. They already knew how to calculate it, you dumbass. So you don't even read the fucking article. All the article says is, guess what? When they made a detector for dark energy or dark matter or whatever the fuck they're looking for, they used the Xeon, and it's a very stable. They used a very stable isotope. Didn't you see that part of the presentation where the guy talks about how stable it is and the most stable isotope in the universe, blah, 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 blah. And they have 3 tons of it in one place. And so guess what? They saw one of them decay. Well, that's what they think they saw anyway. They saw a photon is what they saw. But anyway, and that's what they're saying it was. And so it's miraculous because we saw something that only happens, every 15 years probably in a hunk of 3 tons of something. So it really isn't miraculous. It isn't anything all that interesting. It's just a frickin' piece of radioactive material. Everything's sort of radioactive. Everything has a half-life of some kind. It just happens to be a preposterously big one, but they had a preposterously big hunk of the crap, stuff, gas, whatever. And so they saw one decay. That's it. That's the story. Now the hyper, on the internet makes it into, hey, this is more important than even finding dark matter. Oh, no, it really isn't. It's not important in any way whatsoever. Once in a while, you'll see a horse, let's see, kind of stick his head in another horse's ass. It probably happens 1 in a million horse interactions where the horse actually just sticks his nose right in the other horse's ass. It probably happens now and then. And it'd be really cool if somebody was right there with their cell phone and took a picture of it. And we have a great movie of the horse sticking his head in the other horse's ass. But it doesn't mean anything, fuckhead. Yes, we could all sit there and laugh and oh, that's funny as hell. But it just couldn't mean anything. And so, somebody will hype it and get 1 million views out of it. Horse in horse's ass, They'll clickbait you. But it doesn't mean anything. It's not going to do anything good for anything anywhere. It's not going to enhance any neural state on Earth. And this is zero scientific info here. It's just nothing. It's a complete nothing, as a piece of scientific evidence or helping us get into the future or help us to acquire light speed or some other kind of... It does nothing. It doesn't make a fork forkier or a spoon spoonier or a knife knifier. I mean, this is just shit. And here you are wasting my fucking time again because you can't apply any reasonableness. You got to hype everything too. right? So you're just wasting my time. I'm here to talk about elemental physics. So go back to the beginning where they drew these conclusions like space is bent and photons are waves and things are entangled and I don't know, atoms have energy levels. All the little stupid conclusions they drew and wrote them into fucking stone. They sat there with their chisels and wrote it in stone as if it's the fucking truth, if it's the fucking way it works, when they had nothing as evidence, pretty much. That's what I'm here to discuss. So learn something about that and ask questions about that. All right? I'm not here to debunk every little hypey piece of crap, okay, that the science popular media sells to morons like you. Okay? Idiots buy lottery tickets and idiots read science news. All right? It's made for idiots. All right, anyway. And I was hoping you could simplify how this discovery, there's no fucking discovery. If true, yes, it's true well, look, I don't even know what's true. It's true they saw a photon and they concluded it must be a decay photon. It couldn't possibly, because our thing is 4 miles into the ground, it couldn't possibly be that a single cosmic ray found its way down there and hit our Xeon. Well, maybe that is possible. Maybe that's just as likely as the decay event. But who the fuck cares? It just can't mean anything. All right, relates to your understanding of physics. Well, it can't relate to anything because it's a completely unknown event, okay? I mean, the exact process of radioactive decay isn't exactly anything anybody has a real hard grasp of. And the argument, and then again, this experiment doesn't demonstrate anything about decay. We already know it exists. We already know that this is a rare event. So what the fuck? There's no information here. Does it mean anything? No, it doesn't mean anything. Like every single fucking one of your posts, it leads nowhere. It's a dead end. It's a fucking road to fucking nowhere. Is it all bullshit? It's bullshit for you to sit there and think that every time somebody else says it's important and it's meaningful, that it's important and meaningful. You can't fall for that shit. You have to, I'm sorry, I can't do the work for you. You know, to be smart or to be capable of having good bullshit radar, it takes the work. You have to actually go out and smell bullshit and feel it and touch it and play with it and figure out what bullshit is. And you haven't done any of that. You know, you think you're just going to sit in your fucking chair and somebody else is going to give you all of these tools. Well, it's just not that fucking simple. In some ways it is. I mean, I'm pointing out how it's so fucking goddamn simple and you morons still can't get it. You're still creating this mystique around everything like somehow I have to debunk the hype. I can't debunk hype. I can't debunk the fact that you're all idiots. All right? I mean, there's simple principles. They're just so fucking obvious. Like a bunch of liberals who are for government fucking lotteries or something. Well, yeah, let's steal from the poor and give to one rich guy. I mean, you know, and then they'll sit there and tax the rich and think that makes sense. Well, why are you taxing the rich if you all fucking want to be rich? You know, if you're all buying your hope tickets. You know, jeez, you're all fucking idiots. So anyway, try again. Harder. Alright, now this is just not very readable. Well, we'll give it a best. I guess he's from one of those foreign countries. Wait, couldn't shells make an atom? Fine, but do you have a picture of it? Can you draw me how these shells are made or how these rules are applied? I'm just saying you have physics that isn't physical, okay? You just have magic. Well, let's just say there's a shell. Oh, no, let's say it goes this way and it goes this way. And, you know, and then it goes this way and then it goes this way. So it's could be here, it could be here, it could be here, it could be here. And it's this far out or it's that far out. And, well, this shell is B shell and this is the CW shell and the WF shell. You don't make any of it make any goddamn sense. And so you say an electron goes from here, and all of a sudden it says, fuck you, I want to be living over here in this cul-de-sac over here. And that this event means something somehow. You have no explanation of how it gets there or how it gets out of there. And I'm explaining to you, well, there has to be physics to your fucking physics. There has to be some reason something jumps from one place to a fucking another. All right, and there has to be some sort of mechanism. Somebody has to push the fucking tricycle thing. The tricycle doesn't go if the little 1-year-old is the only thing pedaling it. the swing has to be pushed to swing. I mean, something has to fucking happen. You don't have any happen. You don't have any event in your fucking goddamn physics. You don't have any causes for your fucking effects. You just have effects. You just have a whole bunch of fucking effects, and you don't have any fucking causes. Sorry about the F-bombs. So I'm just saying that no, it doesn't have to be any of that crap. There's other models that work, and they actually have physics in them. So I'm telling you, there's a nucleus and there's electrons. Yes, they're repulsive. You can do this with magnets. You can put magnets in positions, and if they're all north facing, okay, and you can keep them from flipping by putting them between glass or something, you can have their repulsive forces keep them in patterns, okay? All these magnets will find balance. They'll find a balanced geometry, and these will be equidistances, all right? And you'll have a whole bunch of tension in this thing, and if you hit one of these little fellas, all the other ones will vibrate, okay? And if you have a system of atoms where the atoms are connected to each other, you might understand that, see, that you can knock this one and change the pressure, and instead of this one coming back and making photons, okay, the energy to bring it back is pushed into the other atom. So the other atom actually moves an electron, and when it moves that electron, this electron moves, and when this electron moves, then this one can move back, and it doesn't have to steal energy or give back energy to this part of the system. It can give energy back to its own system. So yes, that would be the conduction of electricity, and if you can do that efficiently, then you're not making a bunch of photons. That's the whole damn point. A good conductor doesn't make photons, it doesn't make heat, right? The bad conductor makes a ton of it, because yes, you're jiggling in this electron, and this electron personally gets offended and shoots a bunch of energy back at you. So you hit it, you move it out of its position, it shoots out a photon. It doesn't have to fly. I don't have to take this photon and put it in a different energy level. All I have to do is disturb this energy level. That's all I have to do, is irritate this, and this will say, I want to go back to I had a nice arrangement here. We all liked each other. We were all the right distance apart. My house was a certain distance from my neighbor's house, and his house, and we all liked it that way. And so somebody pushes somebody's house close to the other guy, he pushes into the other guy, he pushes, they all just sit there and say, let's redraw the property lines, because we like this relationship where we all have 20 feet between us. Yeah, it was very nice. But that's all that's happening in these atoms. You don't need to make this complex bullshit story out of it, all right? You can make a nice physical explanation for what's happening. There has to actually be energy that goes in and energy comes out. So there's all these arguments are about conservation. So you don't even have to think about it. Oh, particle wave. You don't have to think about it in any kind of ether versus not ether. You don't have to even think about all that crap. All you have to think about is conservation. And as I gave you the example of the gravity argument, the conservation, you can see you have movement in a direction. When something moves, you can understand, well, it has to absorb something to move. It has to absorb move, right? It can't get moved for free. There's no free move anywhere. So if it absorbed move, okay, to move this way, it absorbed move in that direction, right? I mean, quite obviously, if this thing moves this way, somewhere it took some move that's going that way, right? So where did it take it from? Well, it didn't take it from this fucking direction, quite obviously. So it obviously had to take it from this direction. And what's the consequence of it taking some move? Well, that means this thing gets hit with less move, doesn't it? Duh. Right? That's a real physical explanation, completely conservative. All right, unlike this stupid wooey crap that says, well, because I have mass, I automatically create some kind of magical force where I just put my hand out and say, move. I tell the space what to do, and the space tells the matter what to do, and blah, 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 blah. You have no fucking physics in their fucking goddamn physics. Shit. All right. Wait, couldn't shells make an atom? Yeah, they could, but it depends on what you're calling a shell. It depends on what you're calling it. Some magical woo? No, it's geometry. You can't understand there's a geometry created, right? So if you have the nucleus and you have this tension between these objects, they're attracted to this, and then they're repelled by this, and repelled by this, and repelled by this, and repelled by this, right? So obviously this can't go this way because it gets closer to these two guys, so it reaches a balance, right? And then you have another geometry outside of that, right? Where you could understand that, oh yeah, there's room for more geometry out here. where these guys could all be in attention too, and they're repelled by these guys, but they're still attracted to the proton, right? So you can understand there's geometry built on geometry built on geometry. Now you want to call those shells. I think it's completely unnecessary, and it really just has to do with the energy energy comes back out. So again, it doesn't really matter how you think about it, because it just talks about the fact that you're going to disturb the system with a certain amount of energy, and the fact is you're going to get that energy back out again, unless you can actually remove one of these electrons, from the object altogether, and then create some kind of ion and all that kind of crap. But that's all there is. There has to be energy in, there has to be energy out. So if you just think of it in terms of conservation of tension, right, that you have to have balance or the thing falls apart. It's not a house of cards, but it's a regime where, so what's an example? If you have a ball and you're going to put elephants on the two sides, well, the elephants have to be balanced, or the thing, it's not complicated. All right, in case. So this is where the sentences all go to hell. In case, then let's say another stable shape of an electron formations and have to have the structure. So I really don't know what that is. I think it would have to be responsible for what? Is that a question? I think it would have to be responsible for what? Electric potential or conductivity. Yes, the form of the atom is what's causing the fact that it's a conductor. So the atoms have to be connected in such a way, as I just pointed out, I'll re-point it out. The atoms are going to take pressure that you're going to put in a disturbance. And the idea that, we'll just do an X for the nucleus. The idea is the atoms are in some way connected. That is, they're sharing this electron. This electron is part of this geometry, and it's part of this geometry. And the idea is you're going to disturb this system, and somehow you want to essentially move this whole pattern, right? Because if you can move this whole pattern, well, then you can move this pattern, and you can move this pattern, and you can move this pattern. That's one way of getting the energy in there, because then you're not going to have this problem where you poke this see, the idea is when you make the photon, what's happening basically is you don't disturb the rest of the system. So if you're making a photon, what you do is you push the electron, and the electron is pushed back by the other electrons. And what happens is to move the electron back, right? You moved it this way by hitting it with a force. Well, if it's going to move back again, it's going to give back that force. All right, so that's the problem. That's the photon getting released. That's the heat. You don't want the heat thing to happen. Instead, you want positions to change. So I would argue that the position, when the positions change, that is, these electrons end up getting a little further from each other. All right, now that atom, because the electrons are a little further, that atom becomes positive. Okay, it's magnetically changed. So if you move the electron out, you create a positive. If you move the electron in, you create a negative, you could argue, okay, relative to the proton. And that's really all the electricity is, and that's why it makes poles. It makes dipoles. It makes the atoms polar. And that's what's creating the magnetic effect that is the consequence of the current flowing. So, I have to pause. Alright, I'm back. Try some more. I think it would have to be responsible for what? Electrical potential or conductivity. So, electrical potential or conductivity, those aren't even, those are category errors to sit there and say they're or things, black or white. They're not even in the same category. The conductivity is completely different than what the voltage is. So, voltage. They're not really the same thing. They're not like things. They're not different varieties of the same thing. So the conductivity is basically based on how well the atoms communicate. So their structure, how geometric their structure is. Now, it's not a coincidence that the things that are good conductors are metals, and metals are crystals.
And so that makes sense. The crystals have a real hard geometry, a real steady and consistent geometry. So that all makes sense that they would be more conductive. They'd be better at one electron getting hit here and spreading the energy over the entire crystal. That's the idea. The idea is to take this one event and make an event for everybody. That's conductivity. When you're not conducting, then the event happens and the electron throws the energy right back out again. That's not conductive. That's creating heat. All right, wouldn't shells then be the conditionally flawed assumptions? So again, what? Shells are a lousy assumption in that there's no explanation of them. There's no explanation for this magical rule that they can only jump from their quantum levels. It doesn't mean anything. It doesn't make any sense. The quantum is in the fact that you need a certain amount of energy to move the electron. If you want to get energy you can see back. So if you want to see the energy, you have to send it in a form where we could see it already, right? So if you send in energy that we can't see, you won't get energy back that we can see. That kind of argument. In terms of a reflexive response. Only if you are loading a system with a bunch of little bits of energy and then you put it in a battery, for example, and then you can make a big spark. But you can't make big sparks out of little sparks unless you have a system that can store the energy. Anyway, wouldn't shells then be the conditionally flawed assumptions? I don't know what that, it's not a reasonable sentence. It's not going to work. Whatever. Costs being angles of intersection. Again, you're saying something I can't. You're saying you have some knowledge that somehow there's some flaw in from what you're saying there's a flaw in the idea of energy levels in the electron. But if you accept all of their assumptions, it's only flawed in the sense that there's no physics in it. It's not flawed in the sense that it explains, in a sense, the storage of the energy. The fact that the energy goes in the sense that it's held in an energy level. You now have something in an energy level, and when it leaves the energy level, it's going to give back the energy it took to push it into it. So it satisfies the fact that it's a conservative system, and you have to give back somewhere what you took. But there's lots better ways to describe that mechanism. Anyway. It's not going to work, whatever. Cost being angles by interaction counting possible electrons' relative velocity as the blue is slowed down. See, now he's using my examples and saying, somehow he's talking about the same thing. So it's just incomprehensible. Blue is slowed down, causing protons to cross to the same. So the same with multiple shells is falling apart with energy enough velocity. So whatever the fuck that could possibly mean. Sorry, but there's really no point in doing this translator thing or whatever you did to write this comment. It's just, you're not doing it. It's not working. Not even close. But anyway, I'll read the rest of it, but it's just, there's sort of no point. How would guessing the red to the end protons and less Grinch matter create these problems? Look, I mean, the fact that there's no better explanation for magnetism. I mean, I don't know what the fuck. You can't deal with this fact that you need two forces to create two opposite reactions. I mean, this should be the part where you just say, oh, God damn it, you're right. You have this fundamental thing magnets do. I mean, it's just fundamental that charge does. All right, that if you put two charges next to each other, if you could do this, right, to an electron and a proton, that you have this obvious relationship that if I put the same thing next to it, but inverted, okay, that there's going to be strong attraction here and strong attraction here, and there'll be repulsion this way and repulsion this way, but clearly this distance is a lot longer than this distance, so these things are going to be strongly attracted to each other. And if I put the opposite over here, that that I'm going to have this inverse relationship. Okay, these things are going to hate each other. There's going to be a lot of pressure between them, and they're going to push apart. Now, I've given you a simple explanation for why there's this concept of reflections, okay, that you put two ping pong paddles somewhere and you have a ball bouncing between them that never slows down, all right, that you're going to have more interactions. If I put the two things twice as close together, there's going to be twice as many interactions with the surface, which is the same thing as energy. So I'm showing you a simple way to make energy. Just bring two opposite charges close to each other, and as long as they have a ping pong ball between them, they're going to make more energy. They're going to make pressure that wants to go this way. I mean, I've given you a simple mechanism, and I've just said it's an inverse relationship. So the thing that reflects for one thing doesn't reflect for the other. It somehow leaves. It doesn't do this get trapped thing. All right, and that relationship explains how magnets work. It explains why there's attraction and why there's repulsion, because these two things are inverted. And now you're sitting here making some kind of gibberish counter argument that doesn't have anything to it. I can't even make sense out of it. And why? For what reason are you disputing the fact that this works? You know, how has it failed to work? How would, okay, guessing the red, well, I already read it, it didn't make any sense. There's no, let's see, how would guessing the red to the end protons and less Grinch matter create these problems? I don't know. It's nice if you suckle out the entire place of interactions with what would have all hits, then say another previous hit, then there is so much empty space in an absolute coordinate system. So again, you're disputing the existence of absolute coordinates. So again, you're just creating a bunch of magical woo space. Oh, there isn't a three-dimensional universe, even though every single fucking piece of evidence indicates there is. But no, let's just, whatever you're doing to reality. Oh, fuck this. Especially if an atom model with multiple shells is the jiggle vibration. Yeah, so now all this jiggle vibration, what's causing it? What is causing it? So you're just so, you people just sit there and say things can jiggle for free. I don't need a mechanism. I don't need something to jiggle it. It just does it all by itself. It just magically says, I don't want to be here anymore. I want to be over here. And then when it's over here, it says, I don't like it over here. I'm going back over here. No, I decide I'm going back over here. It just does this for no reason. Right? That's your theory. That's the thing you're defending. This no reason thing. And I'm giving you the counter argument, which is, no, all this stuff has a consequence. If movement was absorbed going this way, well, you got to give it back eventually, okay? Because now, if there's more stuff going this way here, then somewhere in this field, there's more stuff going that way. And those two things might end up getting mixed back together again. Now, certainly there is ways you can let something leave and it'll go very, very far before there's any rebound. You know, light goes way across the whole universe to hit us and then reflect off us and go back to the star it came from. So that's a pretty long distance. It's doing its opposite reaction thing. It's taking a long time to do it. But the universe isn't about time in the sense that it isn't concerning itself for how long it takes. It just concerns itself with the fact that this is a bubble, a closed system, and yeah, things. If you push something this way, the bubble's going to wobble back. So it's like a little blob of water in up in space, and it'll just sit there. You poke it, and the poking will just go on forever almost, because there's no friction. There's nothing to quiet the system down by taking the energy out. So the water will just keep doing this blobby thing for a very, 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 very long time, because the energy is trapped inside. But there's real energy moving. There's real stuff in there making that thing undulate. It doesn't undulate for no reason. Alright, empty space, blah, blah, blah. Especially if an atom model with multiple shells is, okay, we already did this jiggle crap. vibration of an electric potential. So again, you're saying the word electric potential and you have no idea what one is, right? I'm arguing quite simply that electrical potential is movement potential. It's the potential to move electrons, so it's a real thing, okay? So your voltage is really just has to do with how far you displace an electron. So you displace it a lot, well then that's 1,000,000 volts. You displace it a little, well then that's 1 volt. All right, and that's really all that does. So the higher the voltage, the more the magnetic effect, the more you polarize the atom, and the atoms will, obviously the ones that have a lot of displacement, their geometry has been changed big, and it's next to an atom that's this size. Well, yeah, this atom's going to take its energy and put it into this one. So the more I push into this one, the bigger I displace it, the more it has to share with this one, so they both end up being this big, okay? And then the one next to it is, you know, this big over here, and so he's going to share with these two by the same process. This one will share, and then this one will share, and then they'll equalize. And that's why it takes a little bit of time for this electricity to get through something, but that's all the process is. Voltage isn't some magical thing. Again, it's an amount of movement. You've changed something through moving something, and that movement is a real thing. And you can either have that movement turn into the force itself, the photons, the heat, or you can have the movement transfer through the atoms. If it transfers through the atoms, you have a good conductor. If it comes back out at heat, you have a crappy conductor. Let's see. If an atom model with multiple shells is the blah blah blah, we did all that crap. Alright, this vibration of an electric potential. So again, it's just this magical talk. Vibration of an electrical potential. What are you talking about? You can't draw pictures of any of this crap. Alright, doing components to fix drag problem. So again, how does this even relate to that at all? The drag problem is just it's in the elemental physics. None of this stuff is for free. So, you know, yes, if there's a real force, you have to explain how the real force interacts, when I've already gone through all that crap. But I mean, these are simple illustrations of fundamental, elemental things that any idiot, okay, should be able to concede. Well, yes, physics really should deal with these subjects. I mean, they're sort of important. But because they have turned every force into ESP energy, every force is just, I say so, Simon says. I walk up to the door and I just go, Simon says, and the door magically opens with the magical force of my Simon saysing. No, there's something real in the universe. So I've made this point that if you had energy, okay, that was a force, and the force interacted, and the interaction was I'll reflect off this other guy, right? So there's a reflection. Well, how could you tell that from missing? Because guess what? Missing is going to look exactly the same. This arrow is going to go that way, and this arrow is going to go that way. And as I pointed out, if you just make two kinds of force, that is, two things that are distinctly different in some way, then all of a sudden, okay, the universe changes. Because if it's a reflection, you end up with a different reality, okay? The red thing is going this way, and the green thing is going this way. It's obviously different than missing. Missing looks like this, okay, and hitting looks like this. These two things are different. You get it? So now the universe can do something. Something can change in the universe, where nothing could change when this universe was functioning. You couldn't see anything. Even if the little shitheads were hitting each other, you couldn't tell. But this universe, you can tell. These are basic physical mechanics. Then I gave you another explanation. I pointed out, well, this angle thing is sort of interesting, right? Because I can have two things hit each other, right? And there's two ways this interaction can happen. The green thing can end up going this way, and the red thing can end up going this way, right? Now that makes sense, right? That comes in, you know, to conserve the energy. So that's one way these things can interact. But there can be another kind of interaction, right? Where you have these two things coming in at different angles, and they You know, there's components in the 3 dimensions, if you still believe in 3-dimensional reality, all right? And then what they do is they combine their velocities, and the net velocity, which would be this velocity, well, that's where both of them end up going. And that's conservative. You've conserved the momentum by basically having something that can do the math here. So something here did the math. It figured out I have energy in this direction, I have an amount of energy in this direction, and that will create energy in another direction in the 3 dimensions that conserves the momentum, conserves the amount of movement you have in the 3 dimensions, in the sense that this one's obviously all the way in this dimension, but this one has a component in this direction and a component in this direction. And that's where you get your new vector from, is recognizing that everything has a component in the other two dimensions. But that, I'm just saying, this is the basics. It's not much. It's not any more complicated than drawing these simple diagrams and realizing, like Feynman diagrams, it's simple, that's where the universe, that's the level it functions on. It doesn't function on this, I just stick my hand up and go move. It has to function based on conservation of movement. There's movement in the universe, and every bit of movement has an implication. As pointed out, you're not living in some universe where everything isn't connected. No, everything's connected by the fact that we're all getting hit by radiation, and we're all reflecting a certain amount of it. And whether I have a mirror on this side, or whether and this side is unmirrored, isn't that going to make a huge difference to the person who's standing next to me over here versus the person standing next to me over here? Those two people are going to see me in a completely different way, right? That's not complicated, is it? But that explains why physics gets complicated, because now you can have differences. Something as simple as I have one face that's mirrored and the rest isn't. So obviously whoever's in front of me, whoever's facing my mirror is going to see something entirely different than the ones who aren't. Shit. Alright. Fixed drag problem for what I imagine the protons and electrons are less exposed, and not forgetting the math before too. So again, what is this? So they always have to throw the word math in here, as if math solves any of these problems, as if math has anything to do with causes, when it just has to do with identifying effects and recognizing, oh, there's a couple of variables that have something to do with the effect. So yes, obviously you can create all kinds of, there's concepts. I mean, all these equations, all this math only has things like distance in it, and has things like velocity in it. You can have something, a variant of velocity, which is acceleration, but that's, there's only a few things it can have, right? It can have a mass, okay, that is how much it's affected by gravity, how much it absorbs force, how well it absorbs force, that is how well it makes exchanges with force, how well what goes in, something comes out, or whether it stays inside and gets trapped. So there's trappability. You could just make that a new variable, and then you got this idea of time, which was, 100 years ago people were rational and knew time was a constant thing. It wasn't a fucking unconstant thing, and so now they've just used time to make the math, to turn it into some gamma factor, some kind of dopey signal that basically means we're going to pretend frequency equals momentum, like somehow, Volkswagens driving down the road have frequency when they really have a speed on their speedometer and a mass of the car. So we're going to forget what the real variables are and pretend this stupid thing means something when that has nothing to do with it, because in one case frequency does approximate momentum. So then they say all circumstances approximates momentum, when it's just nonsense. The math is just bullshit, okay, most of it. It's just bullshit. And it has no value unless you're doing something stupid like saying, I need to know the exact amount of light that's going to reflect off a mirror at 68 degrees. Fine, the fact that we know the variables that control that doesn't mean they have any clue why. So why mass, velocity, and distance matter, they have no clue. They just know they do. Well, of course they do. Of course we can see that. We can observe it. We can do the experiment. We can say, yeah, it matters how fast they're going. It matters, how aligned they are. We can figure all that out. It's not magic. But it has nothing to do with them being able to create a model that works. Nothing to do with it. Alright, back. Having a little bit of glitchiness here, so try to finish this up. So this video isn't ruined, but we'll see. Annoying. Anyway, so I'll do a little bit more on this muon stuff. Nobody's gonna, like I said, it's kind of, you need the right audience for this kind of argument. But anyway, so the idea is these things rain down from the atmosphere. These guys are going to count how many of these decay events are happening. So as I first pointed out, I don't know how they can tell the decays from the actual entering. So they go through all this work to precisely chart all this stuff so it all looks kind of fancy, and they're making all these little lines and photographs and counting how many decay events take place and all this stuff. And then it gets, so down they go from the top of the mountain. So here's where they're talking about that.
We won't be able to count the survivors of the exact same mesons we counted up on top of Mount Washington.
Right, obviously you can't count those because they obviously had to first hit something to make the photon you saw, so they're already got to be slowed down, right? They had to lose energy to create a photon, so you already have to concede you've degraded them. It's not a magical free, well, we made the photon for free. No, you couldn't make the photon for free, so the interaction probably cost the muon dearly. But anyway, so yeah, it's not going to go, you're not going to be able to count the same ones because they're all used up and they happened, a week ago. So yeah, you're not going to be able to, it's like him pointing out how we're collecting raindrops. Oh, we're not going to be able to collect the same raindrops we collected on top of the mountain. Yeah, well, duh.
Because we stopped them all in the scintillator up there. Fortunately, it doesn't matter, because there was nothing special about these particular mesons. Indeed, we never could have said exactly when any particular one of them would decay. What we use as the meson clock is the average distribution of...
Right, so it's all this average stuff, and they're comparing it to even the decay rate. They're saying that the decay rate they know from the fact that they make the same particle, they're saying. They think it's the same particle. And then they test it by not shooting it the speed of light, and they just sit there and say, we made the particle, how long does it take for it to decay? They're not moving it, right? They're just letting it sit there and say, how long does it take to decay? Now, the fact that something would decay differently depending on how fast you move it, I don't know if that should be a surprise. And I don't know if you need to create 5th and 6th and 7th and 4th and all these other kind of dimensions to explain it. There might just be a connection between velocity and decay rate. Duh.
Decay times of a large number of mesons. So we can count the survivors of another hour's worth of mesons instead, because, as we saw up there, the average number is the same from hour to hour.
Right, so we know the average number isn't the same we know the average number, yes, from hour to hour. It still has some fluctuation, but it's not enough fluctuation to account for anything that matters in this result. Now, but the big difference is obviously at sea level, there's a whole different amount you get hour to hour. So, and the question is are they, what science are they using to account for the difference in the number that you're going to receive at sea level?
We also can't set up at sea level right below Mount Washington. We'd have to excavate a hole all the way down to let the mesons through all that rock.
There's so many issues. So the first one I would point out is obviously on top of the mountain there's lots of wind blowing and there's all kinds of stuff. But all through this atmosphere, the atmosphere is getting denser and denser as you go down the mountain, so it's changing. And it's also turbulence. So there's a lot of turbulence. Well, turbulence increases the amount of interactions you're going to have with something. So the more stuff you're moving by the point, the more likely you are to hit it. So if you're trying to shoot little ducks, the more ducks, in a sense, that are going in, the more chance you have to hit one.
And the Appalachian Mountain Club wouldn't like it. So we're over here at Cambridge, Massachusetts, 150 miles away, and we're counting the survivors of the meson.
So, I guess this would, you can't say that it wouldn't matter whether it's cloudy or not cloudy. I mean, those things have to matter. These things are going through the atmosphere. I mean, obviously, cloud cover has to make a difference in terms of you're creating more stuff for it to have to go through. So to sit there and go 150 miles an hour on a different weather day and say, oh yeah, I should have the exact same number proportionally. Probably not.
Meson's incident at the 6,000 foot level above us here. The average intensity of cosmic rays is the same over horizontal distances of many hundred miles across the Earth.
Right, but not necessarily on the ground. So, yes, above the atmosphere, it's the same, where there's no atmosphere to screw it up. But as you go deeper and deeper into the atmosphere, it matters. And they're just pretending it doesn't matter.
So there are approximately 568 mesons coming down 6,000 feet above us during this hour. Now, there's one thing different about our equipment down here.
On top of Mount Washington, we used a layer of iron about 2.5 feet thick to select our mesons. But between here and 6,000 feet, there's a layer of air equivalent in slowing down power to 1 foot of iron.
So that's, they say so. So how they made that estimate that a foot of iron equals whatever it was, 1,000 feet of atmosphere, who knows? And how accurate it is. And so again, they didn't talk about, oh yeah, well, we had to shave some of these iron blocks because our calculation says it should be 12.5 blocks. No evidence that concerned them at all. So this is just a rough guess, at best.
So to compensate, we've removed 1 foot of iron from our stack.
So they're trying to point out how the two circumstances are different, on top of the mountain and on sea level, and yet they're fundamentally changing the experiment in the sense that they've now obviously moved a foot of iron, and now they're going to be surprised that they're going to see more muons. Now, of course, on the mountain, they would have saw more if they would have removed a foot of iron. If they moved a foot of iron, they would have saw a lot more of them. So now they're just artificially, essentially, creating a higher number because they've now removed a foot of iron.
We've removed that iron in order that the mesons, which stop in our scintillator here, have a speed 0.995 c when they pass the 6,000 foot level above us. That's the same speed which the mesons had when they entered the iron on top of Mount Washington and stopped in our scintillator.
So again, this idea that they stopped in their simulator, the point is now they plowed through a bunch of iron and then stopped in your scintillator, and now you've changed how much iron there is. So again, based on some guess as to how much iron equals 1,000 feet of atmosphere.
Now this is only one of many effects we've had to take into account in this experiment.
Right, lots of effects that you take into account by basically just, who cares? Not a big deal. Not a problem. Because frankly, looking at this experiment, it was engineered to come up with the result they wanted. And that's all. They wanted the simple math to work, and this is the way to make it work.
For instance, not all mu mesons come straight down. Also, a few mu mesons are produced by other cosmic rays between 6,000 feet and sea level. In addition, some mu mesons which stop in our scintillator make nuclear interactions. We believe that we've properly taken all these effects into account and that their effect on our final result is small.
Right. So that's all you have to do, right? You can just make up. Margin of errors are just made up, and that's how simple it is to make it up. You just say, we believe it. That's all it takes. You just say, I don't think it matters. It's pretty much all it is.
Now, let's take a look and see how the counts are coming in.
13.
So so these aren't the mesons coming in. They're counting how many secondary photons they get from decays. So And again, they're looking for a number that's supposed to be around 25, and they're going to get a number like 400 and something. So they're clearly going to imply now that because there's 400 and something, that means the decay rate of the mesons has been altered by their speed, and if it's altered by their speed, it means that time dilated and the entire universe warped in that location, and blah 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 blah.
Expected. Let's go on and take the full hour's count and get some good statistics. 409,
So
410, 411.
they drag it out a little here. So the math they do is really rudimentary. So they have this complex drawing they do of all these events and do all this crap, and then they come down to just doing, 9, divided by 3.
0.7 divided by 6.3 equals 1/9.
There you go. So it's that simple.
These mesons, moving by us at 0.99 the speed of light, keep time at 1/9 the rate they do when they're at rest with respect to us.
As long as you have the right number of iron blocks on there, you can just change that number to 1/8 and 1/7 and 1/6 and 1/5 and blah 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 blah. So it's just an easy experiment to engineer to your results, as long as you can fudge numbers like how much iron equals how much oxygen, and nitrogen. I mean, there's all kinds of assumptions built in that, like somehow it doesn't matter how you distribute the mass in terms of interactions, the interactions still happen. So of course, in some sense, you can argue that density does matter in this case, because the thing is flying through space and is going to hit something, and that's the interaction. So density is important. If the mass has a small density, a small profile, then it's harder to hit. Then your results are going to be completely different depending on whether you're going through steel or whether you're going through oxygen. So if you just do a mass equation, well, if the mass equation doesn't account for the density or the size of the atoms that you're attempting to hit something in, makes a huge difference. The bigger the atoms are, the less likely you are to have an interaction with them that will slow your meson down. And the smaller and more distributed the atoms are, the more likely you are to have an interaction that will slow your meson down.
We used radioactive particles, mu mesons, to show you that moving clocks run slow.
Right.
But I don't want you to make...
So again, moving clocks move slow, is a benign statement, because that's not really what they're saying. They're not saying that moving clocks move slow. They're saying time is broken, and the meson doesn't think it traveled all this distance. It only thinks it went this far, 9 times less distance from the meson's point of view, and all this point of view crap comes into this. So there's no simple statement that, yes, clocks break by this factor when you move them. So anyway, just pointing out how this is pretty fudgy science, that's all. This is the elemental stuff. This is sort of like the two-slit experiment. People cite this stuff as being conclusive proof of something, and the proof is weak. But anyway, so enough of video now. So till the next time and such, so forth and whatnot. Yeah, it's enough. Yep. I'm pretty sure it's enough. Yes. It's not a very scientific conclusion, right? I'm just saying it. Well, I think it's enough. Maybe it wasn't enough. Maybe it needed another 10 minutes. Yeah.